Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll solve a problem on total drag on a flat plate due to boundary layer. So in the last lecture, we have discussed the concept of turbulent boundary layer. So based on that concept, we'll solve this problem. So the problem here, what we have taken, water is flowing over a thin smooth plate of length 4 meter, width is 2 meter at a velocity of 1 meter per second. If the boundary layer flow changes from laminar to turbulent at Reynolds number 5 into 5, that means at this Reynolds number the flow was changed to laminar from laminar to turbulent. Find the distance from the leading edge up to which boundary layer is laminar, and second one is the thickness of the boundary layer at the transition point, and third one is the drag force on one side of the plate, and we need to consider the viscosity of water need to be considered as 9.81 into 10 to the power minus 4 Newton second per meter square. So we can see based on this question, let's first try to draw one diagram here. So the water is flowing over a thin smooth plate. So suppose this is a plate is there, okay, this is a plate, thin smooth plate is there, and over this the water is flowing. Over this the water is flowing with some velocity, okay, and this smooth plate which is present here, due to this there is a boundary layer formation happened here, okay, and the length of this plate is given. So length of the plate is given here 4 meter, and width of this plate, suppose if you can take this concept of width of this one, we can consider this is the width is, that is 2 meter is there, okay, and here we can consider the boundary layer up to some distance, it will be up to some length, it will be like laminar zone will be there, or laminar boundary layer will be there, suppose, and after that laminar boundary layer converted to turbulent boundary layer, okay, and suppose this is the up to this distance, so the distance we don't know, let's calculate this one, so that is x, okay, and this is the total length, that is L equal to 4 meter, that is given, and the velocity of this fluid is given, that is 1 meter per second, and here let's consider a point here, suppose this is E point, and this is F point, and this is G point, okay, these are the 3 points are there. So based on this problem, let's do the solution here. Now see, water is flowing over a thin smooth plate, so this is the thin smooth plate, and this is the water which is flowing, and this point is the edge point, leading edge point, okay, of 4 meter length and width 2 meter, velocity 1 meter per second. So you can write down the data given here, short I write L equal to 4 meter, then width you can write this is B, small b, this is 2 meter, and similarly velocity U I can write this is 1 meter per second, and similarly next is if the boundary layer changes, flow changes from laminar to turbulent. Now see, this is laminar, okay, up to what distance we don't know, just have taken some distance from laminar to turbulent changed, the Reynolds number given RE is given 5 into 10 to the power 5, okay, and the next one is last one, you can see viscosity of the fluid is given, that is mu equal to 9.81 into 10 to the power minus 4 Newton second per meter square. So these are the data given, okay, and from this we need to find out 3 terms is given, 3 points is given. First one is the distance from the leading edge up to which the boundary layer is laminar, that this x value we need to find out. So this is very simple. So based on the Reynolds number like formula, we can calculate this x value, that from this leading edge up to what distance the laminar existing, okay. So as per this one, we can write the laminar boundary layer exists, like consider that is x point, so we know that we can write Reynolds number equal to rho ux by mu, okay. So we can write x equal to Reynolds number, this is 5 into 10 to the power 5 into mu equal to this one 9.81 into 10 to the power minus 4, and this is divided by 1000 into 1 meter per second. Now if you solve this one, okay, it's very simple. Now see, this 3 point and this is 3 cancelled, 2 is there, so 2 again, 2 here cancelled, so minus 2 is there, so 10 to the power minus 2 is present now, okay, this is 1, leave it. Now this one, if you multiply 9.81 into 5, 9 into 5, 45, 8, this is 4, 45, 4, 49. So near about 49 will get into 10 power minus 2 is there. And so you'll get this one 0.49. It may be some value like 0.5 something will be there. Let's write it in meter. And this is, we are getting in meter. Now we can write this is 490 millimeter. Okay, so the distance from this leading edge here in terms of meter, if I write, this is 0.49 meter. 0.49 meter out of 4 meter, this much distance was laminar boundary layer. Okay, now the second point is given thickness of the boundary layer at the transition point. Thickness of the boundary layer at the transition point. So thickness of boundary layer at the point where the boundary layer changes from laminar to turbulent. Okay, so what is the thickness of the boundary layer? That means what is the delta? So boundary layer thickness is nothing but that is delta. So delta need to be calculated based on the Reynolds number. Reynolds number is what? This one. So for this one, we need to consider the delta equation from the Blasius formula. So that is nothing but 4.91 into x divided by, this is root over of RE x, and this one, this formula was given by Blasius. This is no Blasius solution. Okay, and so very simple, we can calculate delta equal to, this is 4.91 into x value already we have calculated, this is 0.49 meter, and this is root over of Reynolds number, that is nothing but 5 into 10 to power 5. Okay, so this one we need to solve it. So 4.91 into 0.49, 2.409, 2.4059, 2.4059 divided by, and here we can write, this is 5 lakhs root over of this, so 707, 70710. This is 707.10. 11 we can write also. Now 2.4059 divided by 707.11, 0.0034. So we can write this is this one 0.00334, I think. Yeah, 34. So this is 34, this much meter. So this one we can write, if you want to write in terms of millimeter, so we can write this is 3.4 millimeter. Now the height of this thickness, that means boundary layer thickness, is here delta equal to 3.4 millimeter or 0.0034 meter. Okay, this one we let it write 1. Now this is second point. Third point is, this is delta, we got it. Third point is what we need to calculate, the drag force of one side of the plate. So here the concept came, drag force. The drag force on one side of the plate. Two side means 2 will be multiplied in one side. So one side will be calculated, that is enough, one side of the plate. So this one will be solved by considering two things. We need to consider the laminar boundary layer. So we need to write the drag due to laminar boundary layer plus drag due to turbulent boundary layer. Drag due to turbulent boundary layer. So two things need to be taken. So suppose this part is the A part, and this is B part. Let's solve this in two terms. Like first one, the A point. A point is what? The drag due to laminar boundary layer. Drag due to laminar boundary layer. So laminar boundary layer from here to here, E to F point. This is E to, we can say, F point. So that is the formula, drag force is there, that is F from E to F equal to, we know this formula, half into rho U square into CD. So CD is the what? We can say that coefficient of drag. Okay, and this is the CD also need to be taken from the Blasius solution of laminar boundary layer. So that also we have derived previously, and this is actually 1.328, and this is root over of Reynolds number. Okay, so this one, if you solve this, finally you will get, let's solve this one, 1.328 divided by 707.11. You'll get 0.00187. Okay, we got here 0.00178. Now, directly I have written actually, because Reynolds number value we already square root of this already we have identified. So this one will get 0.001878. Okay, so this is the CD value. Now, remaining what U value given, rho value known, area need to be calculated. So area of the plate is nothing but, what is the length of the laminar boundary layer existing, that is 0.49 into the width, that is nothing but B. So 0.49 into 2, that is nothing but 0.98 meter square. This is the area. So just put the value in this equation. Now we can put the value in the equation. So finally F, we can write FEF equal to half into, we can write this is rho, that is 1000, rho U square is nothing but 1. So 1 square is, there is no value in that. So half rho into A into U square. So A value 9.98. So now we'll write this value of area, that is 0.98, and U square velocity is 1, so no need to consider that. And remaining value is CD how much, 0.001878. So CD equal to 0.001878. So this will be give you final drag force. Okay, final drag force for the laminar one. So this one we can multiply directly. Here 1000 is there, 1000 into 0.98 and divided by 2, 0.92. So this is 0.92 Newton. Okay, this is the drag force up to the laminar boundary layer exists. Now the second point here we need to consider, second point or B point we can consider here. What is that? The drag force due to turbulent boundary layer, so that is existing from F point to G point. Okay, and so this one again two things are there. One is the drag force due to turbulent boundary layer from E to G point, from the leading edge from E to G, and minus the drag force due to turbulent from E to F, that need to consider. So here what I meant to say, see the total length is there. Okay, so the flow started from the leading edge, but we are considering that laminar turbulent boundary layer from here. Now when you calculate this drag force, the drag force due to turbulent boundary layer from F to G point, so how to calculate this? So that can be calculated, the drag force due to turbulent boundary layer from E to G, means from starting from leading edge to G point, and where you need to consider that turbulent boundary layer started from here by neglecting the laminar boundary layer, minus this one, minus this this boundary layer formation or turbulent boundary layer in that point. FD, the drag force due to turbulent at the E to F point. Now E to G point, this is drag force due to turbulent from this is E to, okay, E to G we have done, E to G and E to F. Yeah, E to F, this is correct. Now we need to find out this. So this one we can write, first one Again, here also again two terms came, like the drag force at this point E2G for turbulent. That is nothing but we can write this is half rho a u square into CD. Okay, now CD here there is a different value. The difference is in the laminar condition also same formula we have used, but here we have taken the laminar boundary layer condition, CD was different. Now though it is turbulent condition is there, in this condition our CD formula will be different. The coefficient of drag will be different. That is nothing but 0.072 divided by root over of Rex. So this one we can find out. So let's write down 0.072 divided by directly I'll do one thing, 7.0.11, 1 point something we are getting. Okay, now this is the value of CD, 0.072 okay, REL to the power 1 by 5. Anyway, okay, no, not root over this one, this is actually to the power 1 by 5. Okay, to the power 1 by 5. So this one will get 5 lakhs to the power bracket start 1 by 5. So 13.79 or 13.8 I can say. So this one 13.8 divided by 13.8. Yeah, this is the value. Will get something like this, 0.00 will get value. Now here the value Reynolds number we cannot consider the previous Reynolds value what we have taken, because the Reynolds number that is 5 into 10 to the power 5 what is given, that is for the laminar boundary layer. But for the turbulent boundary layer again we need to calculate the Reynolds number. Okay, so this value cannot be taken for this one. Now what we'll do, Reynolds number need to be calculated here. So the Reynolds number we can write, this is REL, suppose rho UL by mu, and this one we can write this is 1000 into 1 into the length is 4 and mu is this is nothing but 9.81 into 10 to the power minus 4. So this is 4000. I can directly write 4000 into 10 to the power 4 and divided by 9.81. Correct? So we can solve this, then we'll get the Reynolds number actually. So 4000 divided by 9.81 into this is 40 lakhs 77,000 471. So that means we can write this is 40.77. This one we can write 40.77 into 10 to the power 5. Now this Reynolds number will be used here. Okay, so we can write this is 0.072 divided by 40.77 into 10 to the power 5 to the power 1 by 5. Then we'll get the CD value here. Okay, because the Reynolds number what was given that is for laminar, now we are doing for turbulent, so that is different. So this one will do directly to the power bracket start 1 divided by 5 bracket close 20.99, that is 21 also can be considered. So 0.072 divided by directly 21 you do 0.034. okay, 0.3 you can consider. So finally we are getting this is CD equal to 0.0, what we are getting, let's see. Yeah, we'll get 0.00, yeah, 072 is there. Yeah, 4.7 this one. This is 40 point or 4.7 4 is there. It's what we have done. 4000 into this one divided by 9.81. Yeah, 10 to the power 4 if I consider here, then 4 1 2 3 4 on. So you can write 5. One more 5 is going to be this one. So 40 point, yeah, correct only 40.77. Now this one, what I have done, 1 divided by 5 bracket close. Yeah, 20.99, that is 21, correct only. Then 0.072 divided by 21. Yeah, okay, here we got 0.00342. Yeah, correct one. So here this is 0.00343. See, single mistakes can be done, full problem wrong. So anyway, that is coefficient of drag what we got here. Now again we need to write here, this is F we have calculated for the EG point. Now we need to put the value here, F EG for turbulent, this is equal to, as we have written here, this is half into rho 1000 into area. We know that this is length into width B, and into u square. U square is 1 square, that is leave it, and 0.00343. Finally, we will get some value. Let's solve it. So this value already there. So multiply along with this 4 into 2 into 1000 and divided by 2, 13.71. So the force we got here 13.72 Newton. Similarly, the force from EF, now we need to calculate EF turbulent, and here what we have calculated, EG turbulent. So here also same thing, like half rho into area we need to consider here from E to F point, okay, into U square into CD. So these are the things we need to consider. Now here area of EF need to be considered, that is EF, what is the length into width. So EF length is nothing but 0.49 into 2, that is 0.98 meter square. Now here this coefficient discharge also we need to calculate like this by here. Now we can consider this is 0.072 divided by the Reynolds number value. Here we can consider 5 into 10 to the power 5. Okay, 5 into 10 to the power 5 to the power 1 by 5 will be there as usual. Okay, so that will need to be considered. So here again we can, let me write here, half into 1000 into area here 0.98 into u square, that is 1 square, and this is coefficient discharge. Previously something we got value, anyway I not remember that one, so I'll do it again. This is 0.072 divided by 707.11. 707 was there, let's see previously, yeah, 707.11 is there. Now this one 0.072. Okay, this is not root over, that is to the power 1 by 5, sorry. Okay, anyway, 5 lakhs to the power bracket start 1 divided by 5, 13.79 13.79 0.0052. So here we can write CD equal to 0.0052. This one we can get this value 0.52, that is CD value. Now we can put the value and we can get it here. What is the final one is there? So now EF, let's solve it and write it. How much we got? Already we got this one. Multiply 1000 and into 0.98 into 1 square, that is there, and divided by 2.558. So this one, let me write, this is 2.558 Newton. Okay, now we need to write out the FD, the drag force due to turbulent boundary layer on from F to G point. that is nothing but this one, these two equations what we got here. So that is nothing but we can write F from E to G minus F from E to F, okay, for turbulent. So very simple. I can write this is like 13.72 Newton minus 2.558 Newton. So finally we will get some 7, this one 13 minus 2 11 and 72 minus 558, that is nothing but we'll get some 163 or 162 something will get like this. Okay, so this much Newton. And finally this is FD on the plate, we can write on one side, so that is nothing but we can write again FD due to laminar boundary layer up to F plus the FD due to turbulent boundary layer from F to G, so that is nothing but what we got previously, the same thing we need to write here, 0.92. This is total drag force. The total drag is nothing but 0.92 plus this 11.164. Okay, if you add these things, this is 12 point, we'll get here 4, suppose 4 is there, then this is 5 and 6 0, and this is 956, something will get like this. Okay, this much Newton is there. So this is the total drag force on one side of the plate. If it is called as a two sides, then two need to be multiplied here. But we need to see these are the points like drag force due to turbulent boundary layer and drag force due to the laminar boundary layer. These two terms are very, very important. So I hope you understand how to solve the problem in this type of conditions. Still, if you are having any doubt regarding this, you can give a comment on the comment box. Thank you all.